Hi, everybody. Here we are in Hogwarts, and we're doing 1.2. We're now in again. We're in the applied discrete structure textbook, and we're doing 1.2 basic set operations. And here we go. Let's get down and dirty, and let us begin. So first of all, now much of what we're going to do today is stuff you've seen in the past. Don't worry about it. That's cool. So I'm actually going to. I think for some reason, I think it'll work out better if I'm gonna get rid of my image. It just makes it easier for me a little bit, and might make it more visible for you. Anyway, so intersection. The intersection of two. Oops. The intersection of two sets, which we use a symbol sort of like an upside down U, is the set of all elements that are in both A and B. So you could write it that it's the set of all x such that this two dots also means such that x is an element of A and x is an element of B. So and means intersection. For example, if A is a set 1, 3, 8, and B is a set -9, 22, 3, then A intersect B is the set containing the element 3. So the intersection of two sets is a set. It's not the intersection of two sets is not 3. The intersection of two sets is the set containing 3, because the intersection of two sets is a set itself. That's why we're calling it an operation. Just like if you do an operation on two numbers, you get another number. So you do an operation on two sets, you get another set. And let's say we look at the system of simultaneous equations such that x plus y equals z and x minus y equals 3. Well, this can be viewed as an intersection, because if A is all the xy's such that x plus y equals 7, there are many of them, because 1, 6, -2, 9, so on and so forth. Xy real numbers, of course. And B, well, not of course, but real numbers. And B is the set of all xy where x minus y equals 3. Again, it could be 5, 2, so on and so forth. -1, -4. I think that would work. And equals 3. So these two sets. Now, if you quote graph them, these two sets are lines in the plane, and their intersection, A intersect B, is the set containing the ordered pair 5, 2. 5 plus 2 is 7. 5 minus 2 is 3, and that's the solution of the system. But it's really an intersection of two sets, because I can look at all. You see, what we think of, what we've always thought of as lines in the plane, can be thought of sets of ordered pairs. You see what I'm saying? And now this is the intersection of those two sets. So again, it's just a different way of thinking about. These are things we've seen before. It's just kind of a different way of thinking about it. That's all I'm trying to say. It's just a different way of thinking of it. These okay. I always say to my students that graphing is like a marriage of algebra and geometry, because really you could do this purely with algebra. It's purely an algebra, two algebra equations. That each equation has an infinite solution set, and you want to find the intersection of those two infinite solution sets, and how that's all algebra. But then you can quote graph it, and you get a geometric figure, which in this case is a straight line. And I always say that graphing is like the marriage of algebra and geometry. You're creating geometric figures with algebra equations. So it's just something to think about. Anyway, the intersection of the integers and the rational numbers is just a integer, because every integer is a rational number. So when I take the intersection, I'm just taking the rational numbers, which are also integers. By the way, in general, we're going to see, this is actually an example really of something more general, that if I intersect a set with one of its subsets, I'm just going to wind up getting the subset. It's just going to equal the subset. Okay, if A is 359 and B is -58, then A intersect B is the empty set. Because if there are no common elements, there's nothing, 3 is in A, but it's not in B, -5 is in B, but it's not in A, and so forth. These two sets are what we call disjoint. And if you don't believe me, let's look at the next definition. Disjoint, if two sets of disjoint, if they have no elements in common, that is A and B are disjoint if A intersect B equals 0. And that, by the way, is what a partition is. A partition is when you separate a set into disjoint subsets. But those disjoint subsets, the union of those disjoint subsets has to equal the entire set. Then it's called a partition. Okay, speaking of union, what is, what is the union here? So if A and B are sets, then the union is all the elements that are in A or B. I just want to underline the and over here. That's okay. And so A is a set of all X such that X is an element of A or X is an element of B. So if A is equal to 258 and B is equal to 7522, then A union B is 258, 722. Notice that I did not repeat the 5. So there's a 5 over here and a 5 over there, but I don't write 255 or 722 or 258, 7520. I don't put in the 5 twice. We eliminate the duplication. Now the union of Z and Q is the entire Q. So again, this is just a specific example that if you take a union of a set and a subset, you're going to get the entire bigger set. When you take the intersection, you're going to get the entire smaller set. And the union of A with the empty set is just the set A. What will be the intersection of A with the empty set? The answer is the empty set. Okay. Now, a lot of times in math, we need to define what we in set theory call a universe. And in other words, a set of elements under discussion. Like, for example, if we're talking about a real valued function, then the universe might be all real numbers. So if the set A is equal, if A is equal to the set X, such that 81x to the fourth minus 16 equals 0, contains different elements depending on what kind of numbers we allow to use in solving equations. The set of numbers would be our universe. For example, if the universe is the integers, then A is empty because there's no integer that makes this true. However, if the universe is a set of rational numbers, then A could be 2/3 or negative 2/3. If the universe is the set of complex numbers, if it's a set of real numbers, I'm going to have the same thing, 2/3, negative 2/3. But if it's a set of complex numbers, that's my universe. If that's what we're dealing with, then it could be 2/3, negative 2/3, 2i over 3, and negative 2/3 I. So the universe or universal set is a set of all elements under discussion for possible membership in a set. We normally reserve the letter U for universe and general discussions. You see that, by the way, when we talk about the set of, we want to find real solution, find real value solutions, find integer solutions, find complex solutions. So that's really that's our universe. All right. Next, moving right along, set operations. We're over here. Set operations and their Venn diagrams. Then do you make a diagram? You get it. So I just did there. So when working with sets, as in other branches of mathematics, it is often quite useful to draw a picture. And there's a very famous type of picture we use called a Venn diagram. And I'm sure you've seen these before, but let's look at an example. So here's a set A. I don't even need to tell you what A is right now for this example. A is some set, B is some set. This shaded region represents A intersect B, because if you notice this shaded region, it's inside the A circle and it's also inside the B circle. Hence, it is the intersection of A and B. So it's a visual representation of A intersect B. And this guy here is a visual representation of A union B. Because notice it has everything that's in A, everything that's in B is all shaded in. So this is a visual representation of A union B. Now, all right, fair enough. The complement of a set. The complement of a set is all the elements that are not in that set but are still in the universe. So in Venn diagram speak, oops, hold on a second. Hold on. Where'd my Venn diagram go? Give me 1 second to sort this. I really just explained the bottom part. The top part is saying that the complement of A relative to B, otherwise known as B minus A, is a set of elements that are in B and not in A, and that's B minus A. When you talk about, I was really explaining the second the end part where it says if U is the universal set, U minus A is denoted by the complement of A, and it's everything that's not in A. Let's see if we can get some Venn examples. So this is B minus A because it's the set B, and I'm taking away anything that's in A. So all I have is a little chunk of B, or just the parts of B which are not in A. That's B minus A. And so if my universe is 1, 2, 3, ... 10, and A is 2, 4, 6, 8, 10, then U minus A is 1, 3, 5, 7, 9. In other words, all the odd numbers. A minus U is going to be the empty set. Because here's A, I'm taking, now how can I take away more than what's in A? It just means anything that's in U that's also in A gets taken away. So, and then everything else also gets taken away. So it's all just taken away. Well, basically, since A is a subset of U, I'm taking away everything, so I'm left with the empty set. Now, if U is equal to the set of real numbers, then the complement of the set of rational numbers is a set of irrational numbers. And if I take the real numbers and get rid of all the rationals, I'm left with all the irrationals. As we mentioned, the rationals and the irrationals form a partition of the reals. The complement of the universe is the empty set, and the complement of the empty set is the universe. That's kind of it's very Zen-like, but it's actually true, makes sense mathematically. What just happened? Just jumped. Okay, I'm going to see how that happened, but it did. Okay. Let's see. We did that. D we did. E we did. Okay. If B is a subset of A, then A minus B is as shown in figure 12, 1, 12, 14. And where's 1, 12, 14? This here is the complement of A. It's everything that's in the universe, but not in A. And this here, this is A minus B right there. So this is A minus B, where B is a subset of A. So it's everything that's in A, but not anything that's in B. Now, there's a cool thing called symmetric difference, which looks very nice when you draw it out. Symmetric difference is the union minus the intersection. So just to show you a picture of that, it's going to be this. Because the union, as you remember, was this whole thing. The intersection is the middle part. So if we cut out the middle part, cut out the middleman, then we get just the ends, the ears over here, sort of the floppy elephant ears, I don't know. That's called the symmetric difference of A and B. And I noticed there's some cool examples. Okay. And that looks like that's it for, that's it. Okay, well that concludes this fabulous video, and we will see you guys next time. Actually, before we do that, I just want to look at some of these examples here. I skipped this, so I want to go over it. A is 138, B is 248. The symmetric difference of A and B is 1, 2, 3, 4. So these are all the things that are in A or B, but they're not in both A and B's. Notice, which winds up being everything except for the number 8. And the symmetric difference of A with the empty set is A. The symmetric difference of A with itself is the empty set. Again, very Zen-like, but very true. The real numbers, symmetric difference with the rational numbers is the irrational numbers, because it's all the real numbers which are not rational numbers. I'm sorry, it's the real numbers and the rational numbers minus the intersection, but taking away the intersection is taking away all the rational numbers. You're left with just the irrational numbers. All right, well, that concludes this video, and we'll see you guys next time. Bye, everybody. It's been a lot of fun.